Recording, rolling. It is Thursday, January 30th. All right, so I want to do a little bit of Doppler with you guys. Doppler effect. Got a demo. All right, and then trying to find my poster for that. All right. Oh, a few days back, I think could have been about a week ago. I gave you guys these chapter 13 puzzles. You guys have these chapter 13 puzzles. All right, so let's do this the same way that we did it last time, which is as long as you guys are solving these in class today, I'll put the points in for you. Right, and if you're absent or not working on it, then well, I'll have you turn it in another day. But if you're working on it in class today, then I'll give you guys the points for these because there's well, a lot more work at home you guys got. I'll get you guys your next take-home quiz by the end of class today. So probably the last couple minutes of class, got a take-home quiz for you. And then also AP Classroom. Now this has been open for, I think a week or two now, but let's go over that on Monday. So can you guys have that done by Monday? Right? You guys got all that? Right. And then my plan for tomorrow is I'll print an FRQ for you guys with it. All right, so you guys got kind of what we're doing? All right, so got a couple other things too. Tonight is the Science, Technology, Engineering, Math Career Showcase in the cafeteria at 6 o'clock. So if that looks interesting to you, it says connect with UCF, Boeing, Brevard Zoo, Collins Aerospace, and more. So tonight, 6 o'clock in the cafeteria. And this I posted to Google Classroom, I think a day or two ago. It's Drop Savers poster contest from Cocoa Utilities Department. So there's a poster contest, and they have categories for different grades. So like high school is a category. Yeah, they're prizes. So certificate of participation, display of artwork in City Hall, and Cocoa publication and social media, $25 gift card. All right, so prizes for making a poster about how to save water, basically. So if you want to read the details on that or submit something, that's posted to Google Classroom. All right, let's do a little Doppler here. So I have a piezo here. I've got it in this ball of string, this big old puff ball. All right, so let me connect this. And here, I don't know if this shows up on the video or not, but you guys listen real close. Do you guys hear a tone? You guys hear that? They're going. Right. Now, it's a little better. Sometimes it takes a couple of times to get connected right. Try again. Yeah. You know what? Here, I'm gonna play you guys a demo while I'm getting this for sure set. It's gonna explain what I'm about to do here. All right.
You're like a bird, you're looking right down in the water, and there's a bug sitting there. And this is a lake that's perfectly smooth. But now what the bug starts to do is the bug starts to jiggle up and down. And when that bug jiggles up and down, that bug is a vibration, yeah? And that's vibrating on a nice surface, yeah? We're going to make what begin with a W? All right. We're going to make waves, gang. We're going to make waves, okay? And the waves kind of look like this. Where I draw the line, that represents like the crest of a wave, like it might sort of be like this. You kind of see what I'm saying? Okay, so this represents the crest of the waves. And the waves go out in all directions. And the fact that they're circles is kind of evidence that they go out in all directions at the same speed. Isn't that true? Like if it went faster over here, then the wave would sort of be like that, yeah? Okay, so the circles are evidence of the same speed. Okay, now what would be the frequency of the waves compared to the frequency of the vibrating bug? In other words, if you put your hand here, blip, 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 the waves would hit your hand, yeah? Certain frequency. How would that blip, blip, blip compared to the whoop, whoop, whoop of the bug? Same. Isn't that right? The frequency of a wave is the same as the frequency of the vibrating source. Makes sense, doesn't it? Let's suppose now that the bug swims in this direction. Yes. What the bug is going to do is the bug is going to swim in the direction of the waves that it's producing, and it continues to vibrate a little bit, yeah? Wouldn't the wave pattern look something like this? Kind of be seeing that?
Yeah, see how the bug's swimming, it's catching up to the very waves it's sending out. All right, so we got relative motion now. All right. All right, so let me give us another shot here. Come on. All right, connect that one. Well, all right, let's go back to this then.
In fact, what direction would the bugs be swimming, gang? I mean, you can tell it's going that way, right? Well, the bug might be at rest and the water's going this way. I mean, motion is relative anyway, yeah? Okay, now if I put my hand over here, would I get a higher speed wave, a lower speed wave, or the same speed wave? Check your neighbor. And make sure you're listening to the question that's being asked.
All right, guys, the way he phrased that question, he talks about the wave speed. Guys, once that ripple leaves and it's going, what is that? Is that? Oh, that's this thing. All right. Guys, once that ripple's going through the water, doesn't it just propagate at whatever speed it's going? Yeah, it does, right? All right. All right, yeah, I gotta fix this again. Yeah. All right, I'm gonna see if I can get this going while it's going right now. All right, so if I swing this around, you guys listen. I don't know if it's working. Do you guys hear a pitch change? Great. Of all times. All right, hang on. That's what we do. Hang on. Pause this. We're gonna see what's going here. All right, so you guys heard the pitch rising and falling as that was wheeling around. All right. All right, so you guys notice the speed of the wave doesn't change once it's going through the air. The speed is whatever the speed is. It's already been released into that medium. If the speed isn't changing, but you hear something different, you're perceiving a different what? It's not a different speed. It's a different. Okay, yeah, wavelength or frequency could be good, right? Wavelength and frequency. Because all right, wavelength and frequency.
How many people say, hey, the speed of the wave is going to be the same? Yeah, that's right. The speed of the wave doesn't change. What does change, gang? How frequently that wave encounters you is different, yeah? So I can get a different frequency. When I put my hand here, higher frequency or lower? Can you see it? Over here.
All right. All right, so he's getting at something called the Doppler effect, right? Okay, so there's an equation goes with it, goes like this.
Interruption, Hawk. We appreciate your cooperation during the drill. At this time, you may resume normal activity.
All right, so in terms of frequency, like what frequency does this guy hear versus, let's say there's a car horn going beep, beep, something like that. Okay. Now, if you're along for the ride in the car, you perceive that frequency as if the car was parked, it wouldn't sound any different, okay? Okay, but if you're out on the sidewalk, well, it depends if it's a car approaching you or going away from you. And if it passes, it sounds like, meow. You hear that pitch shift, okay? So what are these, what's this observed frequency compared to the source frequency? And it depends on motion. So I got the speed of sound right here, speed of sound, speed of sound. And notice if nobody's in motion, the velocity of the observer, velocity of the source, if both those are zero because they're just standing around, what does that fraction turn into right here? 1, yeah. And then the observed frequency matches the source frequency. You guys see that? Okay. Now, if one or both are in motion, if this guy's running back or forth, or the car is driving, well, one way or the other, right, towards or away from the guy, you guys see a couple of plus or minuses here, right? So you have to be able to navigate this. Let's see if you guys can. Oh, now, if let's start with if the observer is stationary, this B could be 0. If the car's headed towards the observer, then right, critical thinking time. You guys ready for critical thinking? The car's headed towards the observer. Okay. Does this observer perceive a higher or a lower pitch than normal? Higher pitch. So if it's like a 400 hertz car horn, maybe he perceives like 500 hertz. It's going to be something higher. Okay? And how do you get a higher how do you make this observed frequency higher than the source frequency, like 500 here, if 400 here? Okay? Would you have to add or subtract down here? Subtract. Because if you subtract, it makes the denominator smaller, which makes the overall fraction bigger than 1. Right? If it's like 1.25 times 400 gives you 500, right? Something like that. Yep.
What if you go faster than the sound?
Faster speed of sound. Can you do that? Can you go faster than sound? Faster sound. It's called see faster, greater, supersonic. Oh, God, ripped off a Superman cape right there. Supersonic. Yeah. And if it's supersonic, yeah, it will create this cone type wave, right? And then you guys ever heard of sonic boom? Right. So if you're standing right here and let's say a rocket goes over, right, faster than sound, right? Once this cone wave passes you, that's where you perceive the sonic boom. It's boom right there, right? You guys ever heard like Mach 2, Mach 3? Right, that's the speed of, well, say in this case, the jet compared to the speed of sound. Going Mach 2, that's twice the speed of sound. Yeah.
So if you had 3 observers all standing like a quarter of a mile away from each other.
Yeah.
They would each perceive a sonic boom at just a different time.
Yeah. If you got 3 guys right here, you got boom for the first guy, boom for the second guy, boom for the third guy. Yeah, there you go. It's like that. All right. Huh? Do you guys see this cone wave right here? This cone wave, right? Because if you're going less than the speed of sound, maybe you hear an increased pitch change, but none of these waves overlap, right? Right. But once you surpass the wave of sound, see these 2 pictures side by side? Like this one, like the waves never cross, right? This one, the waves cross each other because the source is traveling faster than the very sound waves it's sending out. Yeah. So you get this cone wave, right? Right. Which I want to show you guys a quick demo of this too. You guys can actually see this cone wave, right? But back to here. Oh, because I'm not going to do very much of this Doppler effect with you guys because AP does not ask about this, but I think it's good for exposure just to know about it, kind of be able to navigate this, and also be able to figure out how things work. I mean, guys, you're going to have lots and lots and lots of puzzles in your life from who knows all what corners, and something good to get out of this class is well, how do you break things down and think about things, right? Right. So let's do some other ones. Guys, if the car's driving away from the observer, should you add or subtract down here? Add. Yeah, because that, like if there was a guy standing right here and the car's going away, I somehow need a lower frequency. So I need a larger denominator. So I'm going to add down here, plus v source. Okay. Now, what about the numerator? Oh, suppose I have the observer is running towards the car. Guys, if you're running towards the car, is that going to be an increase or decrease observed frequency? Increase. And how do you get increase on top? Add or subtract? Add. Right. And if you're running away from the car, should you subtract on top? Yeah. All right. All right. So that's how I always navigate this Doppler formula myself. Solve these. Good thing to know is here's a little bit different perspective on this, like what's plus and what's minus. If both of these are going to the right, you can do minus and minus. Right? If they're both going to left, it's like plus and plus. If they're headed towards each other, it's going to be opposite signs. Right? So it's a different way to think about it. It'll get you the same correct answer there. Right. Let me see if I can dig it real fast. That supersonic demo. I think where is supersonic? Here it is. All right. And at some points you could do you guys see that cone wave right there? We go back. Right. So there's a few of these throughout this video, but you see one. Oh, did you guys see it? You guys see that cone wave? Right there. It's a real shallow cone. You guys see that? Right. It's real shallow because it's just going just barely faster than the speed of sound. Maybe like Mach 1.1 or something like that. Okay. Actually, if you knew that angle, you could probably calculate how fast the plane's going, right? Compared to the speed of sound. Yeah.
I have a plane that's going so fast that by the time like the sound like starts emitting, it's already past that point. Like if it's going so ridiculously fast that it's past the sound wave that it's producing.
Yeah, that's exactly what you just saw. Yeah,
Like
that is this.
But still, the
Yeah.
first sound wave is around that plane, so if it's going like even faster to the point where the sound waves are actually behind it.
Yeah, like here, like when the plane was back here, it would have been emitting the sound wave that turns out to be this one right here, right? Right. And see how by the time the plane is here, it's outpaced that sound wave. That's exactly what this is.
Okay.
Yeah. Right. So anytime you're going faster than sound, you get that kind of wave. All right. Right, so again, not going to show up on the AP exam. Good to know about. All right. All right, let's look at you guys' 13 puzzles. Yeah, as long as you guys are working on these today, give you guys some points. Great. Ooh, did you guys see a mass on a spring? You guys, here's another mass on a spring. I see a lot of masses on springs. There should be Okay, there's another Massimo spring. There's gotta be some pendulums in here, right? Number 34, there's a pendulum question. Number 42. Hey, didn't we put together some of these oscillating graphs the other day? Right? Now this is position versus time, got some kind of oscillating motion there. Right? And then, yeah, I got some questions. All right, so guys, all these puzzles you guys can solve with the posters that we've gone over last few days. Let's see if I can dig out the main ones real fast. This one's probably pretty good to know. Right? Guys, be able to linearize graphs. Right? We've done lots of graph linearization. We did some of that for some recent labs, but know those. Right? Here, this one's going to be really handy today. Right? Guys, I see 3 variables here: time period, mass, and spring constant. I don't see anything about gravity field. I don't see anything about amplitude. Right? So those might affect other things like maximum speed, but right. And the other one that's good to know is this one right here. That's actually where we started this about a week ago. Okay. All right. So go ahead. Yeah, make good use of time, solve lots of puzzles. Yeah. Yeah, I'll give you this one right here. All right. And hang up this recording. And you guys remember AP Classroom? Ended today. I'll get you guys your take-home quiz. And tomorrow I'll have an FRQ for you guys.